Okay, so I welcome you all, and today we are going to talk about variational principle. Of course, variational principle has its touch from classical physics as well, but we do extensively use variational principle in quantum mechanics because most of the problems in quantum systems are very complicated problems. You cannot directly solve these problems. You cannot directly have solution of these problems. And if you rightly remember, before variational principle, we extensively discussed perturbation theory. And perturbation was a means to basically understand a system in which you were trying to disturb a system with a small magnitude of the perturbation. And, and you calculated that perturbation in the framework of the known Hamiltonian. You knew exactly how to solve that problem. But now we are in a domain where we don't know anything about the system. You have not a known story of your system. And this comes up in the framework of variational methods. So we make use of variational principle to understand, to get the approximate results of a system. Now again, if we go back to our curiosity kind of story, I want to share another imaginative story, and the hero of this story is Isaac Newton. If you rightly remember, it was nearly 1665 when there was plague in Britain, and it was a dangerous disease that was spreading all around, and people were dying. And it was the time when Isaac Newton, he probably he didn't turn up. He was inside his house. He was inside his cabin, where he was curious. He was curious about the problems. And this time, his curiosity was not about the fall of an apple that led him to the universal of gravitation. It was not about discovering the calculus, which in modern times, even the kids from America, they find it difficult when they are in higher secondary grades. But this time, the man looked at the same flame of a candle. You have a candle and a flame is buzzing out of this candle. Now the point is, do we actually come up with the research when we suppose I have something and I intend to search for something? We believe that the greatest things in the science have not happened this way. The greatest things have happened only by looking at the problem. How keenly you are looking, how keen you are about looking a problem. Now, what am I trying to express here is that this candle has a flame and flame has a shadow. And the man sitting inside his home, not allowed to come out of his house because plague is outside, and he is looking at the shadow of the flame of this candle. And when he looks keenly, see, it has happened accidentally. He did not plan a review of literature for it. He did not write down that I'm going to solve this problem. It was his curiosity. He looked at the shadow of the flame. And what he found? He found at the edges of that shadow, he could not find the complete darkness. He found a mixture kind of light on the edges of the shadow. You are in a dark room, the plague is outside, a candle is lit in your room, and you are looking at the shadow of the flame of this candle. And what clicks the man? It clicks. Why there is a mixture kind of shadow at the edges of this flame? So you see, there is a lot of curiosity. Everybody has a candle. Everybody lights it. They use it. But this man is focusing the dynamics of the shadow that's produced by the flame of this candle. So this hits his mind. It clicks him. And what he does, he goes for a hole. He develops a pinhole. It was a time, till this time, people completely believed that light is white. It's a pure light. It was the complete understanding of the people of that time. And what he does, he doubts that mixing. He doubts the shadow. And what he does, he makes a hole. And he manufactures a shutter on it so that he can close it, he can open it. Then in front of that hole, he puts a prism. And when he puts a prism, he allows the light to fall. He allows the light to cross the hole. And what he finds? He finds the splitting of white light. It's not an ordinary outcome. It's not an ordinary thing that has been discovered by this man. All of your astronomy from A to Z is dependent on this spectrum of light. This is the only information that we are receiving on the planet. Because light is showing different colors. And different colors bend at different angles. So each color has its own characteristic wavelength. It has its own characteristic angle at which it bends out of the prism. And what we are doing in modern times in astronomy, we are receiving the electromagnetic spectrum. And it's this electromagnetic spectrum that's giving us the information about the universe. Is there any other way? For that, you are using very sophisticated telescopes. You have telescopes on the surface of the planet. You have telescopes orbiting the Earth in the form of James Webb Telescope. But see, this small result, it seems extremely small, but it has given birth to all modern sciences that you have. And it has given you an edge to realize that what cosmos is, what universe is. You have a complete measurement chart. You can say this is the observable universe. Because only the light that you can receive from, there may be universe beyond the observable universe. But we are reporting only that what we receive. Right? So it's a small flicker basically. It's a small kick. And concentrating that click can lead to a very, very fundamental reality that we don't understand. So our target is variational principle. Let me introduce you with this. What we have, we would not include any mathematics here. Then I will start with the mathematical argument. So it has very, very strong implications in quantum mechanics because it's a principle that is giving you an approximate energy of the ground state of the system. And you don't know anything about the ground state energy of that system. You can use this variational principle. It's a very powerful method in quantum mechanics. And of course, everything in quantum mechanics we have approximate apart from some idealistic problems like particle in a box. So, so for approximating the ground state energy of the system, you can approximately calculate the ground state energy. It provides a way to estimate energies when exact solutions are not possible, exact solutions. So this makes a difference between the perturbation and the variational principle. In perturbation, you solve your problem in the framework of what is solvable, right? But that's not the case of in case of variational principle. It's something you are shooting something without knowing anything about the system. So this method originates from classical mechanics, I told you, and was adapted in quantum mechanics by the pioneers like Schrödinger and Heisenberg. Okay, and it became a cornerstone in computational quantum physics. Most of the times when you do the computational physics, variational principle is a very basis. So what is the basic idea now here? So you have a system, you don't know anything about the system. So you don't know anything about the system. What you do to solve that system? You guess a trial wave function. You choose a trial wave function. And then you calculate the expectation value of this wave function. The expectation value of the Hamiltonian will always be greater than or equal to the true ground state energy of that system. So what you do, you choose a trial wave function. Then you calculate the expectation value. You have a Hamiltonian of that system. You calculate that using expectation value. And what it does basically is this allows us to approach the exact value by improving our guess. So that means you are guessing a wave function. You are guessing a trial wave function. And your guess cannot be always right. Okay? So you choose this guess, and if your solution is close to the ground state energy of the system, close or greater than that of the ground state energy of your system, then you are on the right track. So what you calculate this energy. You calculate this energy using the trial wave function. The trial wave function that you have introduced. You calculate the Hamiltonian. Once you calculate the Hamiltonian, if this E comes greater or equal to the ground state energy, then you are on the right track. And if you get it less than that of the ground state energy, you're on the wrong track. So variational principle is very important here in how pure, how accurate your guess is. That leads you to the approximate close result of the problem that you are discussing. So what you have here, basically, you have an inequality, okay? So the energy that you are calculating, it's either equal to the ground state energy or it's greater than that of the trial, the ground state energy. So now if you look at this graph, can you see it? You have a graph here, okay? You have energy versus trial parameters. So now if you look at the dotted line, this dotted line is an indicator of the true ground state energy. And now you see, you are choosing a trial function that's given to this point. You are choosing another trial function that's given to this point. So these 2 points are very far. Are you getting my point? So they are bad trial wave functions you have chosen for your system. And then you have a trial function that's exactly matching to the ground state energy. And something that's close to this ground state energy. They are both acceptable, okay, depending on the type of the problem. But it should not be far as like these points. It should not be like this. So this graph can tell you exactly that where you are guessing a trial wave function is close to the problem that you are discussing. Are you getting me? Okay? You get this graph? Okay. So, now point is why it works. The principle is based on the fact that the true ground state minimizes the expectation value of the Hamiltonian. Okay? The true one. See, you have hydrogen atom with one electron. Now, if I talk about the helium atom with how many electrons? 2 electrons. Okay? Helium. Now the problem is complicated. Okay? So what you can do, you can come up with a trial wave function. If your trial wave function is close enough, okay, your ground state energy will be greater or equal to, the energy that you will calculate using that trial wave function will lead us to what? The true energy of that system, the energy that's close to the true energy of that system. So any deviation from the true wave function increases the energy. So you will see that there will be more increase in the ground state energy of the system if the trial wave function you have chosen is not an accurate, is not something that's very close to define your system. Again, choosing a trial wave function. So what we have, the success of the method depends on the choice. So it's not like that you will do anything. Okay? So you have to choose 1 out of 100. You have to choose 1 out of 10. So it must have a physical logic in your mind that what you are going to choose for it. Or you getting my point? You are not going to choose a door for the cabin which is very, very big so that it will not fit to your cabin. So again, you have to choose here. You have to use the skill so that your results are very close to the reality. It should incorporate the symmetry of your problem. The trial wave function that you are choosing, you cannot choose any damn thing. It must be symmetric. It should symmetrize. I will not make a car kind of object for the door because I see the cabin and the cabin demands a rectangular thing. Suppose this cabin is rectangular. I will not choose a circular door for it. So what is important here is that it should incorporate the symmetry and the boundary conditions of the system. Okay? To which extent your system is bound and what are the bounding natures. So you can see here, suppose I choose this graph, you can see it has a complete resemblance with the Gaussian distribution function. Now, most of the nature that we have behaves like this. Now, if the y-axis is the amplitude and the x-axis is the position, now you can see you have the dotted lines. These dotted lines are coming out of the trial wave function that you have chosen. Okay? And you have the solid line. The solid line is the result of the true value. And you can see the deviation. And you can see that there is a larger deviation at the core. But when you go to the edges, you see the two things are overlapping. And you see the peak is overlapping. So in this case, the trial wave function is a very good approximation because the results that you are obtaining for your problem, they are very much close to the true value of your system. Is this clear? Clear? Okay. So it is an approximation. It has applications to approximate the energies of atoms, molecules, and solids. Come on. This is what makes it very strong. You can exactly solve the problem of hydrogen atom, but you cannot exactly solve the problem of hydrogen molecule. Can you do that? No, you cannot do that. Even if you try to do it analytically, you will come up with the trivial solutions, and for that you may have to use a dozen of 200-page copies. No, that's not the case. Variational principle, it paves the way. It gives us the measures of energies of atoms, molecules, and even solids. So you can see the credibility of this method. It's a very strong tool in condensed matter physics. It's a very strong tool in molecules, where you have chemical kind of things. Okay? Essential in fields like quantum chemistry and nuclear physics. Your nuclear physics, where you always approximate your system, okay? It has very strong applications in those frameworks. Now, talking about the hydrogen atom, suppose. So a simple example is approximating the hydrogen atom in ground state energy using a trial wave function. Okay? So with an adjustable parameter. So now you have a trial wave function. You would like to incorporate in your trial wave function a constant, but that constant has to be adjustable. Suppose I call something psi equal e to the power of alpha r. So alpha is what? Alpha is an adjustable constant. You would like to adjust it. You understand that the symmetry of the problem is like, say for example, a e to the power of alpha r. But now you have to work on the alpha so that the result is very close to the ground state. Is this clear? So by minimizing the calculated energy, we get the close to the exact value. So how do we minimize? Suppose I calculated the energy using variational principle. How do I minimize? Because I can calculate this alpha by minimizing the system. How we minimize the system? Any idea about the maxima and minima? How do you differentiate mathematically? Yeah. Assume that you have a maxima or a minima. Yeah, you take its derivative and you say the derivative of that physical quantity is equal to 0. So using that condition, you can calculate these values. It has role in computational methods. It's the foundation for many numerical methods like Hartree-Fock density functional theory, what we generally call as DFT. These are very powerful mathematical tools. So variational principle has a role in both of these models that we use in computations. Strength, it's simple in concept. It's very simple. You choose a wave function. You choose a trial wave function. Works even without full knowledge of the system. You don't know anything about the system, but still it works and provides an upper bound to the ground state energy. At least it gives you the upper bound of the ground state energy of the system that you are discussing. Limitations, obviously it must have limitations. Its accuracy depends heavily on the trial function. As I said, as we discussed about it depends on the trial wave function, the choice, what you choose for your system. And you cannot directly find the excited states without the modifications. You have a system going into the excitations. You cannot use variational principle to calculate the excited systems. What do you mean by excited system? You have hydrogen atom in ground state. Okay, your electron in the first orbit can be excited to the next. Okay, now it fails actually to give you the excited states, but you can make some minor modifications where you can still have an information about the higher energy states of that system. So methods like Rayleigh procedures, they extend the variational principle to more complex problems. These are the methods, the numerical methods that we can use incorporating variational principle and can solve the complex problems. So this principle is a versatile and intuitive tool for tackling quantum systems, where exact solutions are not possible. You see, not possible. You cannot exactly solve these problems, right? So what does it mean? What does it mean mathematically? What am I trying to say? Is it the lost? Yeah. What does it mean? It means, it means variational principle. What do you do basically is, you choose a trial wave function, say psi. You choose it. And you operate this trial wave function on the Hamiltonian of that unknown system. So you have a Hamiltonian operator. Okay? You have come up with a trial wave function, say ket of psi, okay? And you operate this trial wave function on this Hamiltonian. What does the operation mean here? It means you calculate the expectation value. And the expectation, so E trial, what is expectation? That is psi, h cap, and psi. This is divided by psi and psi. So the trial wave function that you have chosen, you normalize that wave function, right? When you normalize that, the denominator of this will be equal to 1. Okay? So what you calculate ET is the expectation of psi, h, and psi. And if the energy that you have calculated, if this E trial comes out to be, if it comes out to be greater, the E trial, if it comes out to be greater or equal to the ground state energy of that system, then you are on the right track. Okay? So the trial wave function you have assumed, it works for your problem. Otherwise, you have to change it. Otherwise means, if this ET is less than the ground state energy of that system. Is this clear? Okay, any questions you can ask me? Yes? Come on. Come on. So in the next class, we'll be solving some of the problems based on variational principle. Okay? I hope everybody is fine. And in this video, I'll be talking about the application of variational principle that we have already discussed in the previous video, and I'll subject this variational principle to calculate the ground state energy of hydrogen atom. And if I repeat the variational principle in quantum mechanics, it basically provides a way to have approximate a ground state energy of a system by choosing a trial wave function. And then what we do is we minimize the expectation value of the Hamiltonian, and then this principle accordingly ensures that this expectation value is always greater or equal to that of true ground state energy. In case of excited to ground state energy. Now here in this video we have to I would like to estimate this. So the goal of this video is to estimate the ground state energy of one-dimensional hydrogen atom. So we're treating it as one-dimensional, and using this variational principle. And to start with, we can have a one-dimensional Hamiltonian for hydrogen atom, and what we do here is we ignore basically the spin of the electron, and we also ignore the relativistic effects. So what will be the Hamiltonian? The Hamiltonian is simply kinetic energy operator plus potential energy operator. Okay, so this is my Hamiltonian, and I can write down this h as minus h cross square by 2m d2 by dx2, this minus. So the potential energy between the nucleus and the electron is minus E square by 4 pi epsilon naught x. So this is my first term, and this first term is basically the kinetic energy operator, and the second term is the potential energy operator for the Coulomb attraction that exists between the nucleus and the electron. And x is because it's a one-dimensional case, so we have taken just one component. Now, the important thing here is that what we have to do is we have to choose a wave function. We have to choose a trial wave function. Trial wave function. And let us choose this trial wave function that reflects the expected behavior of the system. Now, I think the common choice here will be to choose this trial wave function psi of x as a e to the power of minus alpha x square, where this a is the normalization constant. I should write this is normalization constant. And what does that mean? Okay, a is a constant and it has to be calculated using the normalization. And alpha that is here, this alpha is a variational parameter. It's a variational parameter. It's a variational parameter. All right. This is the parameter that we are supposed to adjust to minimize the energy of the system. Now, what do we mean by normalization is that means the integral from minus infinity to infinity and psi of x whole square dx equals 1. This is our condition. This is what normalization means. And we can substitute the value of this wave function into this normalization condition as minus infinity to infinity a e to the power of minus alpha x square whole square dx is equal to 1. Now, proceeding from here, what we will have is this a will come as a square, and what will be left, so we will have a square integral minus infinity to infinity, and then e to the power of minus 2 alpha x square dx will be equal to 1. Okay, so this 2 will come here, so this is e to the power of minus 2 alpha x square dx equals 1. A is a constant, this a is out, and we have a standard integral here. This is a standard Gaussian integral, that is minus infinity to infinity e to the power of minus 2 alpha x square dx. This is standard Gaussian integral, and we will directly substitute its value, and what's its value? Its value is under root of pi by 2a. So we can use it here in our equation of normalization. So this is a square times under root of pi by 2a equals 1. The eagles are banging outside. Okay, so from here I can calculate this a. So what will be a? So a will be 2 alpha up divide by pi whole to the power of, it has whole to the power of 1 by 2, so it will become whole to the power of 1 by 4.
Now this is my A, and I can write down my trial wave function. What's that? Psi of x is a e to the power of minus alpha x squared. A we have calculated, and we can write down this wave function. So what will be that? That will be psi of x is, instead of a, I will write 2 alpha by pi whole to the power of 1 by 4 e to the power of minus alpha x squared. So this is my wave function. Okay, now what is important is that I have to calculate the expectation value. And in order to calculate the expectation value of the Hamiltonian, and my Hamiltonian is made of kinetic energy operator, and it's made of potential energy operator. So I have to calculate the expectation value of kinetic energy operator. Now, in order to do that, so what I have to calculate? I have to calculate the expectation value of kinetic energy operator. And in doing so, I think the right choice is to calculate the double derivative of this wave function. So if I take its first derivative, so this is d psi by dx with respect to x, what I'll get, I think here I will have the internal derivative of this exponential function, that will be 2 alpha. So this 2 alpha by pi whole raised power 1 by 4 times this is whole constant here, and here the derivative will give me minus 2 alpha times e to the power of minus alpha x squared. So this is my first derivative. And what will be the second derivative? So here I'm missing something, because it's alpha. This is d by dx of alpha x squared. So differentiation of x squared is 2x. So this is alpha 2x. So this is alpha x and 2 alpha and x. That should be the case. So now so this whole thing is a constant, okay? And we can keep it out. And now if I have to take another derivative, so I will differentiate this again with respect to x. So I'll get d2 psi of x by dx2. I will not write this thing, okay, for the time being. I'll keep it as say something like zeta. So this is zeta times, now I'll have UV rule here to be utilized. So what I'll have say x as its into differentiation of this. The differentiation of this will give me the same thing, that's minus 2 alpha x e to the power of minus alpha x squared, and then v as its, that means e to the power of minus alpha x squared, and the differentiation of x will give me 1. Now let me move on to the next page so that I can write down this. So I will have d2 psi by dx2 will be, so I will use this zeta as well now. So that is 2 alpha by pi, 2 alpha by pi whole raised power 1 by 4. Then I have minus 2 alpha out. Then inside what I'll have, I will have this minus 2 alpha x squared. Okay, so this is minus 2 alpha x squared e to the power of minus alpha x squared, then plus e to the power of minus alpha x squared. Okay, this should be the case, and we can see here what we will get is we will get 2 alpha by pi whole raised power 1 by 4, and what you will have, this will be minus minus plus, 2 2s are 4, this is 4 alpha x squared, then minus, okay, so this minus will make it minus, so minus plus is minus, then 2 alpha, and what will be out is e to the power of minus alpha x squared. So this is my double derivative of this wave function dx2. And now what we can do is, if we have to calculate its expectation value, now let me call the expectation value of kinetic energy as T. So T refers to the kinetic energy. What will be that? That will be minus h cross square by 2m, then integral minus infinity to infinity, then we'll have psi of x, then d2 by dx2, and then psi of x. So it should be complex conjugate of it, then you'll have dx. And we can use d2 by dx2 in this integral, and after evaluation its value will come, this whole thing will give us alpha. So we'll get minus h cross square alpha by 2m. So this is my expectation value of kinetic energy. So I may call it 1 for the time being. Okay, then what we are supposed to do is we are supposed to calculate the expectation value of the potential energy. And what we have is we have the potential energy operator. So now expectation value of potential energy term. And what is that? That is, we can write down the expectation value of potential energy as minus e square out 4 pi epsilon naught out, then integral minus infinity to infinity. Then we will have psi of x by x, the magnitude of x whole, not whole, the square of this wave function, and divide by magnitude of x, which is linked with the potential energy operator. Okay, so here we will have dx, and on evaluating this integral we will get the expectation value of potential, and using the same approach and using the value of the integral directly, we will have minus e square by 4 pi epsilon naught, then under root of 2 alpha by pi. So this is our expectation value of potential energy. So we have calculated the expectation value of kinetic energy. What is that? That is minus h cross square alpha by 2m. Then we have calculated it for the potential energy. That's minus e square by 4 pi epsilon naught under root of 2 alpha under root of 2 alpha by pi. Now what is, so I should write down this, I should write down this E. The total energy is then the expectation of the kinetic energy plus the expectation of the potential energy. All right, so so I can write this E equal to, so this E will be equal to, what was that? That was minus h cross square alpha by 2m, then minus e square by 4 pi epsilon naught, then under root of alpha, under root of 2 alpha by pi. Now what we have to do here is we have to use the condition of minimization. That's the part of the variational principle. Now to find the optimal value of this alpha that we have the variational parameter incorporated in the trial wave function. Then for that, to calculate this value, for that we have to minimize the energy. So if we have to minimize the energy with respect to alpha, so for calculating alpha, we minimize energy with respect to this variational parameter alpha. So for that, the derivative of this E of alpha with respect to alpha must be equal to 0. And to take the derivative of this equation with respect to alpha is the easiest thing a person can do. And by doing so, after minimizing, what we find out is that this E approximately, call it approximately, its value comes out to be nearly, will be the right thing, minus 13.6 electron volts. minus 13.6 electron volts. So this value is very close to the known exact value for the hydrogen atom in the ground state. So we can see the beauty of using this variational principle. I think I have misquoted the sign here, because on evaluating this integral we come up with some negative and this becomes positive. One of them has to be positive, only then we will have negative. So this is positive, and finally what we obtain is we obtain the ground state energy, the approximate ground state energy of what we call this as hydrogen atom. Now in the next video, I think I'll be discussing the same thing for a simple harmonic oscillator. I mean, we'll use variational principle to calculate the approximate energy of the simple harmonic oscillator. Now let's proceed to another problem where we will choose a trial wave function for solving the problem of simple harmonic oscillator. So what we have here is a simple harmonic oscillator. We would like to solve the problem of simple harmonic oscillator using variational principle to get an exact idea about the variational principle. Now what we have to do, again in the same fashion, we have to estimate first of all the ground state. The eagles are again in action. They're blowing whistles. Okay, so what we have is to estimate the ground state energy of a simple harmonic oscillator using this variational principle. And immediately we would like to write down the Hamiltonian. So Hamiltonian for harmonic oscillator is kinetic energy, that is minus h cross square by 2m d2 by dx 2 plus 1/2 of m omega square x square. So this is the Hamiltonian for one-dimensional harmonic oscillator, and we can easily estimate out that the first term in this Hamiltonian is the kinetic energy operator, and the second term that we have here is the potential energy operator for the harmonic potential. And I think all of you know the basis of this, that 1/2 of kx square, where from we come up to this result. Now, what's the next thing? I'll choose the same trial wave function as I used for solving a one-dimensional hydrogen atom, the energy of hydrogen atom. I would like to use the same Gaussian trial wave function as I have used in the previous problem. So my trial wave function, so I choose it to be psi of x is ae to the power of minus alpha x square. And what is alpha? Alpha is the variational parameter. So this alpha is our variational parameter. And this variational parameter and a is the constant, and this constant has to be calculated using normalization condition, and I will directly write down the result for this normalization because we had evaluated it in the previous video. So this a, the value of this normalization constant a comes out to be 2 alpha by pi whole to the power of 1/4. And so that we have the normalized wave function, normalized trial wave function. So that will be psi of x is 2 alpha by pi whole 1/4 e to the power of minus alpha x square. And we have calculated the double derivative of this Gaussian function in the previous video, and we have calculated its expectation value because it's same as it was in case of hydrogen atom. So I'm sorry. So I can so the expectation value of the kinetic energy operator, say T. So what is that? That comes out to be that is basically minus h cross square by 2m, then integral minus infinity to infinity psi star d2 by dx2, then psi of x, and then dx. Okay, and on evaluating this, the expectation value of this kinetic energy operator comes out to be h bar square alpha by 2m. So this is our kinetic energy operator that is inculcated in the Hamiltonian of this simple harmonic oscillator problem. Now the next thing is to calculate the potential energy. Now for potential energy, we have to calculate the expectation value. Say that potential energy is V. So the expectation value of V is going to be, I think, 1 by 2m omega square will come out. Then we will have integral from minus infinity to infinity. Then we will have x square, and then we will have psi of whole square dx. And on evaluating this integral, the expectation value of this potential energy comes out to be 1 by 4 m omega square by alpha. Now I can write down the total energy. So what will be that total energy? The total energy will be sum of the kinetic energy, expectation value of the kinetic energy, and the expectation value of the potential energy. And I think this is calculated as h bar square alpha by 2m, and this is calculated as m omega square by alpha is E. Now, what's our job? Our job is to calculate the value of this alpha, and the value of this alpha can be calculated by using the optimal condition, and the optimal condition here can be, I would like to minimize the total energy. So in order to minimize the total energy, what we have dE by d alpha must be equal to 0. So let's do in this case, let's find the value of alpha. I didn't do it in the previous case because it's easy, you can do it. So now let's go with it here in this case. So what is E? So I would like to write down d by d alpha times E. E is h bar square alpha by 2m plus m omega. This is m omega square by 4 alpha. So here it has to be 4 alpha. Okay, so m omega square by 4 alpha, this has to be equal to 0. Now let's differentiate. So this h bar square by 2m will be as it's. So differentiation of alpha with respect to alpha will give us 1. Then here we will have m omega square by 4, and then we will have d by d alpha of 1 by alpha equals 0. So we can write down h bar square by 2m plus, this is m omega square by 4. So this is d by d alpha of alpha raised power minus 1 equals 0. So we will have h bar square by 2m plus, I think this will become minus because the differentiation of alpha raised power minus 1. So minus will come here, and you will have m omega square. This is alpha raised power minus 1 will give me alpha raised power minus 2. So this alpha raised power minus 2 will go down. So we will have divided by 4 alpha square is equal to 0. Now from this equation I have to calculate alpha. So I can write down this m omega square by 4 alpha square equals h bar square by 2m. So we can cross it down. So let me take it So this is 4 alpha square h bar square is equal to 2m square omega square. So alpha square will be it will be 2m square omega square by, okay, what will be here? So this will have 4h bar square. So this alpha will come out to be under root of, so this is 2 ones, this is 2 twos, so we will have, yeah, yeah, that's fine. Yes, so that is h bar square by 2m. Yeah. Okay, so here alpha, I think yeah. All right, that's fine. Okay, we have this. Okay, so this will give us h bar alpha square, and no, it has to be alpha. That's fine. No, that's fine. So it's okay. It's fine. It's fine, and it's fine till now. It's fine. So what we will have here is square will go on the other side. So I'll get m, and then I'll get omega, and then I'll get under root 2 and h bar. All right, so this will be our alpha, and now we have to use the value of this alpha to calculate the total energy. So what is our total energy? So total energy is h bar square. So total energy is h bar square alpha by 2m plus m omega square by 4 alpha. Okay, so here we will use the value of alpha. Maybe I have committed some mistake, I don't know. If I have, then you rectify it. So let's proceed from here. So let's go with that approximate value of ground state energy. So for alpha, I have to use the value of m omega by under root 2 h bar, and in doing so you can make this addition between these two terms, and it nearly, so you have to approximate it, it nearly comes out to be h cross omega by 2. So so what's the reality here? What we have obtained is, I think, the exact value of the ground state energy of the harmonic oscillator. So on substituting the value of alpha in that equation leads to the approximate ground state energy, which comes out to be h cross omega by 2. This is the exact known ground state of the energy of the harmonic oscillator. So the variational method that we have used here, it has worked. It has perfectly worked in this approximation. So by choosing the trial wave function and minimizing the energy, we can certainly obtain good approximations to the ground state energy of a system. And this variational principle is especially valuable when solving Schrodinger equation is too complex, or is, I should write, too complex, or I should write impossible. So with this, a very goodbye to all of you. Hello, everybody. We have been taking into account a range of problems based on variational principle, and in this video I'll be talking about I'll be actually executing this variational principle on a complicated problem like an harmonic oscillator. And this variational principle is, as we understand, is a powerful tool that's used in quantum mechanics to approximate the ground state of systems where we know that the exact solutions are very difficult. So for the anharmonic oscillator, the potential deviates. It deviates purely. It deviates basically from purity. Purity, I mean, from quadratic form to the harmonic, from the quadratic form of this harmonic oscillator, and making the problem much more complicated, because we have the kinetic energy term, we have the potential energy term, and there's a deviation in that quadratic term. Now, what approach we would like to execute here is the general approach as we have used in case of hydrogen atom, in case of the harmonic oscillator. So the problem can be set up in the same way, like we have the general Hamiltonian for this anharmonic oscillator, as H is say p square by 2m, then 1/2 of m omega square x square, and assuming the third term to be like lambda x raised to power 4. So this is our Hamiltonian. And the first term, as we all understand, it represents the kinetic energy. The second term, it represents the harmonic potential, and it's quadratic in nature. And then we have the third term here that we have introduced. The third term is lambda x raised to power 4, and this is what introduces this anharmonicity to the system. Now the challenge is here basically the presence of this x to the power of 4 term, and which makes Schrödinger equation unsolvable. It's practically unsolvable analytically, and this is where the variational principle comes in action. It becomes useful. So as usual, what we do is we use the trial wave function. So we have a trial wave, we choose a trial wave function, and the key to using this variational principle is selecting a good trial wave function, and which is our psi trial, if I say psi trial of x, and this function that we choose, it should resemble the exact wave function of the system, and it should also obey some good bounding conditions, like going to 0 as x tends to infinity. Now, for the anharmonic oscillator, a good trial wave function is often chosen to resemble the ground state of the harmonic oscillator, with a parameter that's varied as. So the very trial function, if I say psi of x, is a e to the power of minus alpha x square, that we have been using in the last two cases as well. But this alpha is a variational parameter that controls the width of the wave function in this case, and a is a normalization constant, and what it ensures is that the integral from minus infinity to infinity psi of x, which is a trial wave function, whole square dx, is equal to 1. And what we do here is we apply the variational principle, and the variational principle states, what it states is that the expectation value of the Hamiltonian calculated with the trial wave function provides the upper bound to the true ground state, closeness to the true ground state, and this E trial comes out to be, so this is the expectation of psi, and then h, this is psi of x, then h, and then psi of x. Okay, divide by psi of x and psi of x. And as the wave function chosen is normalized, so we can take off this denominator, and we can write down this E trial as the expectation of the Hamiltonian, psi of x, then h, then psi of x. Now, to find this expectation value, what we do basically is we calculate this E trial. So what we do, we calculate this expectation value as integral minus infinity to infinity, okay, psi star and psi star of x, then you have the Hamiltonian, and then you have psi of x, then we have t of x. This is whole divided by integral minus infinity to infinity psi of x whole square t of x. Now this expression, what happens to it? It simplifies to what? E trial. Should I call it T? Okay, let me put a T here. So E trial, with respect to that alpha that's to be calculated, is the expectation of the kinetic energy plus expectation of the V harmonic, and then the expectation of V anharmonic part. So this is how our energy is simplified to, and this is the kinetic energy term, this is the potential energy term, and the third one is the potential energy term due to the contributions in anharmonicity. Now what we do then, as we did in the previous case, we calculate this expectation value of kinetic energy, and exactly we do it in the same way, like minus infinity to infinity, then you have psi star of x, and then you have minus h cross square by 2m d2 by dx2, and then you have psi of x, then dx. And we have the trial wave function. What's that? That's psi is a e to the power of minus alpha x squared. And we have done in the previous video, we have calculated this a, and we have calculated this alpha, and the things boil down to what we have obtained is that this expectation value of kinetic energy comes out to be h cross square alpha by 2m. All right, and this on evaluating that integral, what we finally find is h bar square alpha by 2m. Now we have the next term, that is the V harmonic, and this V harmonic, it has to be evaluated in the same fashion, minus infinity to infinity psi star of x, then we will have 1/2 of m omega square x square, and we have done it in the previous case, psi of x d of x. And what is the result of this integral? This V harmonic, it comes out to be m omega square by 4 alpha. So this is our expectation value due to the harmonic term. This is our expectation value due to the kinetic energy operator. Okay, operator, and this is due to V harmonic operator. And then we have the next thing is the anharmonic potential. So for V anharmonic, what we have to do the same thing, minus infinity to infinity, then psi star of x, and then we will have lambda x to the power of 4, and then psi of x d of x. And on evaluating this integral and making those calculations, what we obtain here is we obtain this v harmonic is it is 3 lambda by 4 alpha square. So this is your anharmonic term. So now we can write down the total energy expression, and we can write down that total energy expression as total energy. So what will be that we combine all the terms to get the total energy of the function in terms of alpha. So what is that? That is E in terms of alpha is it is h cross square alpha by 2m, and this is the first term, and then plus I have m omega square by 4 alpha, yeah, m omega square by 4 alpha, and the third term is 3 due to anharmonic term is 3 by 4 alpha square. Now these are our terms. Now from this equation, what we have to do is we have to calculate this alpha, and how we calculate it, we minimize this equation. And how do we minimize it? We minimize the trial energy that's coming over here, so that this dE of alpha by d alpha is equal to 0. So to do that, what we do is we take the derivative. So I would like to take the derivative of this equation. Okay, so I will take the derivative. So taking derivative. So what I'll have dE alpha by d alpha will be equal to, okay, what it will be? It will be d by d alpha of this h bar square alpha by 2m plus d by d alpha of m omega square by 4 alpha, then plus d by d alpha of 3 lambda by 4 alpha square. So this is what we do, and we individually calculate the derivative of this, the derivative of this with respect to alpha, and the derivative of this, derivative of this, derivative of this, and derivative of this. So we can easily see here the derivative of this will be h cross square by 2m with respect to alpha. So I can think of, I would like to write it in independent. So d by d alpha of h cross square alpha by 2m will be simply h cross square by 2m. Now the second thing is d by d alpha of m omega square by 4 alpha. So we have evaluated this differentiation in the previous video, and what it will come as minus 1 by 4 m omega square by alpha square. And we have the third term here, d by d alpha of, this is 3 lambda by 4 alpha square, and this will give me minus 3 lambda, okay, minus 3 lambda, because this 3 will come, because when we'll take this alpha square up, it will become alpha raised power minus 2 when we'll take its derivative. So it is, what is it, 4, okay. So when I'll take its derivative, the 2 will come down, and that 2 will cancel this 4 and will make it 2, and you will have minus 2 minus 1, minus 2 minus 1 will give you minus 3. Then this alpha will come back to the denominator, and you will have alpha cube here. And so we have these three derivatives, and we have to set them all equal to 0. We have to add them in accordance with this equation and equalize this to 0 in order to calculate alpha. So what does that mean? That means h bar square by 2m and then minus 1 by 4m omega square by alpha square minus 3 lambda by 2 alpha cube is equal to 0. All right, now in order to solve this, we can multiply this equation both sides by 4 alpha square. So multiplying both sides by 4 alpha square. So what we'll get here is 4 alpha square to eliminate the denominator. So multiplying this whole equation with 4 alpha square will give us what? So what we'll get, you can check it, we will get 2h bar square alpha cube minus m omega square alpha minus 6 lambda is equal to 0. This is what we will obtain. You can check it, and this is a cubic equation. You can see it's a cubic equation in terms of alpha, and which may not have a simple analytical solution, but at the same time this equation can be solved numerically for the specific values of for that we must have the value of h, we must have the value of m, we must have the value of omega, and we must have the value of lambda. All right, so if we have those values, only then this equation can be solved depending on the situation, and using the values of these constants will take us to the result to obtain the value of alpha for this particular problem that's under consideration. So this equation has yielded the optimal value of alpha by solving this cubic equation, and this equation can be numerically solved, and provided you incorporate the values of those constants that are provoked here. Now the optimized value of alpha, whatever the optimized value of alpha will obtain from here, is substituted back into the trial energy function, okay, to give the variational estimate of the ground state energy. That's the purpose basically, and this energy E trial is basically an approximation of the true ground state of the anharmonic oscillator. So by choosing more sophisticated trial wave functions, you can improvise the accuracy of the result for the particular problem. So to conclude this this video, a quick reminder is that using variational principle of the anharmonic oscillator involves choosing an appropriate wave function, calculating the expectation values, minimizing energy with respect to the variational parameter, and then this method provides the powerful way to estimate the energy of the system where the exact solutions are not possible. So with this, I would like to end this conversation. So because depending on all those parameters, you will have alpha, and that alpha can be used in the value of E, where alpha is involved. What is that equation here? Yeah, not this. I mean, here is that equation. So once we come up with alpha, we use that alpha in this, use the values of those constants that are involved here, and we will be able to calculate the approximate ground state energy of this anharmonic oscillator under consideration. So with this, I would like to say goodbye and have a nice time.